Hi, what's up guys? It's YG here. Today I'm going to teach you how to use the Cramer's rule to solve a linear system. We have a linear system right here, and the first step to use the Cramer's rule is to find those determinants. So, solution. Firstly, we need to find the determinant of the coefficient matrix, which is the coefficient matrix here. So D is equal to the determinant. You just pick up all those coefficients from this equations. So 0, 1, negative 3 as the first row, and the second row we have 2, 1, 1. The third row we have 3, 2, 1. To find this determinant, you can use many different methods, such as the cofactor expansion, or the basket weaving, or the that is called the elementary row reductions. And now I want to use the cofactor expansion along the first row. When we use this method, we always keep in mind with the sign table: positive, negative, positive, negative. So 0 is here, and then we plus 1 times the deleted submatrix of this, which is 2, 1, 3, 1. 2, 1, 3, 1. But the sign for this position is negative. So we also times negative 1. Then we have negative 3, the entry, times the determinant of the deleted submatrix, which is this small guy here, 2, 1, 3, 2. 2, 1, 3, 2. And the sign of this position is positive. So that's it. Now we continue to compute this determinant. We have 2 minus 3, which is negative 1, plus, times this negative 1. So it becomes positive 1 here. Plus 4 minus 3, that's 1. 1 times negative 3, that's negative 3. So the answer is negative 2. That's the determinant of the coefficient matrix. After that, we want to find D1. D1 is the determinant obtained by replacing the first column with the column here, 0, 0, 2. So you just replace your first column with that 0, 0, 2, and everything else stays the same. 1, 1, 2. Negative 3, 1, 1. To find this determinant, I want to use the cofactor expansion along the first column. Because the first column has many zeros, so I don't care about these two entries. I just need to work on this. We have 2 here times the deleted submatrix of this, which is the upper right little submatrix, 1, 1, 1, negative 3. 1, 1, negative 3. And the sign of this position is positive. So it's just 1 minus 3, that is 4. 4 times 2, that is 8. So we have 8 here. Then we continue, move on to find D2. D2, you just replace the second column with the column there. So we have 0, 0, 2 as the second column replaced, and everything else is the same as this. Negative 3, 1, 1. And to find this determinant, we also use cofactor expansion along the second column this time, because you have many zeros here. So I have 0, 0, which I don't care, and then this, which is 2, and then times the deleted submatrix of this position, which is you cross out this row, cross out this column, and you're left with 0, 2, negative 3, 1. So 0, 2, negative 3, and 1. And the sign of this position is positive, negative. It's negative, so you times negative 1 here. And we see that we have 0 minus 6, which is minus negative 6, which is 6. 6 times this 12, so it's negative 12. Negative 12. And now we move on to find D3. Now this time we replaced the third column with 0, 0, 2. And the rest of the things stays the same. So we have 0, 2, 3, same as this. And then 1, 1, 2, same as this. And now we expand along the last column. So I have positive, negative, positive, negative, positive. 2 is positive. Now delete this matrix. 0, 2, 1, 1. 0, 2, 1, 1. And cross multiply. 0 minus 2. That is 2. So it's negative 4. Now we have everything ready. We just need to plug in the formula to find the value of those variables x, y, z. Since x here in the equation is in the first column, so we will be using d1 for the value of x. According to the formula, x is equal to d1 over d, which is 8 over negative 2, and we have negative 4. And then y here is in the second column, so we will be using d2 for y. So y is equal to d2 over d, which is negative 12 over negative 2, which is 6. Y is equal to 6. And at last, we have z in our third column, so we will be using d3 for d3 over d, which is negative 4 over negative 2 equal to 2. Now we have our solution here, x equal to negative 4, y equal to 6, and z equal to the positive 2. We can plug in to the original equation to verify our solution. For example, the first one, you have y, plug in 6, right? 6 minus 3 times 2, 6 minus 6, which is 0. So it satisfies the first equation, which means it's correct. Now we can check the second equation in the same manner, and you can see that this is exactly the solution of this linear system. And that's how we use the Cramer's rule to solve linear system. But Cramer's rule also has some limitation. It's not true that every linear system can be solved by using Cramer's rule, because in this expression you have d in the denominator. We know that denominator cannot be 0. So if this determinant is 0, then we will not be able to use the Cramer's rule. For example, in those situations. Okay, that's all.